So in the last session, we found that for every prime p and n an integer and positive integer greater than 0, we have a finite field of order p to the power of n, and every finite field has p to the power of n elements for some prime p and integer n greater than 0. These are the two results we established earlier. Our next question is can we have a finite field that is algebraically closed? Meaning, if you take a finite field, every polynomial in that finite field should have a 0 in it. So you should not have any irreducible polynomial. So let us assume, let E be a finite field. What does that mean? That means E contains p to the power of n elements for some p prime p and integer n greater than 0. And we also know that these elements of E are the distinct zeros of the polynomial x to the power of p to the power of n minus x. Let us take this as R. We can take R elements, and this is R, and this is R. Now, let n is an integer greater than 0. Then we have another field E dash having p to the power of Rn elements. definitely, and is an extension of ZP. This is also an extension of ZP. If it's a finite field, it is always an extension of ZP. So E is an extension of ZP. Both are extensions of ZP. Here, this implies E prime has elements, or E prime has E prime contains precisely the zeros of x to the power of p to the power of Rn minus x. That belongs to ZP of x. So we have two finite set E and D dash, E prime. E has p to the power of R elements. E dash has p to the power of Rn elements. Now let us assume that alpha belongs to E. If alpha belongs to E, that implies alpha to the power of R, p to the power of R, minus alpha is equal to 0. And that implies alpha to the power of p to the power of R is equal to alpha. But let us calculate alpha to the power of p to the power of nr. This you can write it as alpha to the power of p to the power of r times p to the power of r times n minus 1. Because if you add this is 1 r, this is minus 1 r, cancel, so you will have n. And that is equal to, this is what? This is alpha to the power, sorry, this times alpha to the power of, so this is equal to alpha times alpha to the power of n, r times n minus 1. And that is again equal to induction alpha times alpha to the power of n minus 2 dash dash dash, that's equal to alpha to the power of alpha to the power of sorry, this is actually p to the power of r n minus 1. This is actually p to the power of r n minus 2. So this will be, finally it will be p to the power of r, and that's equal to this will be 0. This will be 0. So that will be so that means if alpha belongs to E, then alpha is a 0 of alpha to the power of p to the power of nr minus, 0 of x. And that implies alpha belongs to E prime. And what does that mean? That means E prime is a finite extension of E prime is a finite extension of E, and the degree of E prime over E is equal to n. Because the reason for this one is we know that if E is an extension of f of degree, both are finite extension. If E is a finite extension of f having q elements of degree n, then E has q to the power of n elements. And that's exactly what we are using here. And n is actually greater than 1. Here it should be greater than 1. Yeah, greater than 1. Because if it is already 1, then E and E prime are same. What does this mean? This means there is an irreducible polynomial. There exists an irreducible polynomial of alpha over f belongs to f of x, E of x. Because there are some alphas in E prime that is not in E, and which is a 0 of this polynomial. So this polynomial exists in E of x, and if you reduce it, there is an irreducible polynomial. This irreducible polynomial will be a factor of this. So what we found is, for any finite field, we can find an n greater than 1 such that there is an irreducible polynomial of degree n in E of x, which means that E is not algebraic. So there are two results here. One is for any finite field E and integer greater than 1, integer n greater than 1, there exists an irreducible polynomial in E of x. Well, if you want to add one more step here, it is not very clear. What we will do is, what I said is, there is an element in E prime that is not in E, which is a 0 of x to the power of p to the power of n r minus x. But in other words, this implies this is a finite extension, so it's a simple extension. So that means E prime is equal to E of beta for some beta, because if it's a finite extension of a finite field, that extension is simple. So that means there exists a irreducible polynomial IRR, irreducible polynomial beta over E, belongs to same. If you want to add one more step ahead here, that is, so this is a final result. As another result is a finite field cannot be algebraically closed. So for any finite field E, an integer n, there is an irreducible polynomial. Of degree n in E of x. Now let us assume that there are two finite fields of same number of elements. Let E and E prime be two finite fields of p to the power of r elements. Then what can you say about E and E prime? Well, E is a finite field of p to the power of r elements, implies it is an extension of ZP and has precisely the zero of x to the power of p to the power of n minus x. That belongs to Cp of x. Similarly, E prime also has the same element that is the zeros of x to the power of p to the power of n minus x belongs to Gp of x. So for similar argument, E prime is also an extension of Zp, and because it has got p to the power of r elements, E prime contains exactly the zeros of this polynomial. So that means E is isomorphic to E prime. If you take any two finite fields of same number of elements, they are isomorphic. So our next question is, if you are given a number, can we find if there exists a finite field of that order? For example, let's say 603. do we have a finite field which has got 603 elements? So the first thing what we need to do is factorize this if we can. If we cannot factorize it, then it's a prime number. Definitely there is a finite field of that order. For example, if you take 71, 71 cannot be factorized at all. There is no number that goes inside. So 71 is a prime number. E is a prime number, and hence there exists a finite field having 71 elements, and it is precisely Z of 71. But what about this? So what we need to do is first you divide, factorize this. 3 goes in this because 6 plus 3 is 9. So 2, 0, 1, again 3 goes. So it will be 67. So this is equal to 3 square into 67. There are 2 different prime numbers as factors of this number. So this cannot be expressed as p to the power of n. Every finite field has p to the power of n elements for some p and n. So if somebody is asking, do you have a finite field of 603 elements, then no finite field exists with 603 elements. What about, you take another example, 4096. So again, if you know that that is not a prime number, factorize it. So when you factorize this one, 4096 to 2048 to 724 to 512 to 256 to 128 to 64 to 32 to this is 16 8 4 2 2 1 2 3 4 5 6 7 8 9 10 11 12. So this is actually 2 to the power of 12. So this implies there exists a finite field of 4096 elements and is a finite extension of Z2. Our next problem is find the number of number of 18th primitive roots of roots of unity in GF19. GF19 is Galois field of order 19. 19 is a prime number. So this is a finite field of 19 elements. So actually GF19 will be 0, 1 up to 18. So what is the meaning of primitive roots, 18 to primitive roots of unity? Alpha is a primitive root of nth primitive root of unity in E if alpha to the power of n is equal to 1 and for 0 less than m less than n, alpha to the power of m is not equal to 1. That is the definition of nth primitive root of unity. What we need to find here is 18th primitive root of unity. And that primitive root of unity of this one actually sits inside the non-zero elements of GF18 and non-zero elements of GF19. Non-zero elements of GF19 is a multiplicative group which is cyclic. So we normally write it as GF19 star is equal to 1, 2, that at 18. So the 18th primitive root of G19 sits inside this because 0 definitely is not. This is actually isomorphic to, see, this is a cyclic group. So basically, if you can find the generator of GF19 star, we are done. Suppose let alpha belongs to GF19 star such that alpha to the power of 18 is equal to 1, then and alpha to the power of m is not equal to 1 for 0 less than m less than 18. This is what we are looking for. We need to find out an alpha in here such that alpha to the power of 18 is equal to 1, and if you take any lesser exponent, the value cannot be 1. That implies alpha is a generator of GF19 star. GF19 star is definitely a cyclic group. Generator means it has to generate all these 18 elements. But it is difficult to find out a generator from here because it's multiplication. So what we are going to look at is, we are going to find out, is there any field that is isomorphic to this? So there is a field which is isomorphic to this, that is actually Z18, and that contains 0, 1, 17. with this is actually multiplication as a binary operation. Here this is a addition as a binary operation, which is much easier. So the number of generators in GF19 star is same as the number of generators in Z18 because they are isomorphic. This also has 18 elements, this also has 18 elements, and it perfectly obeys the homomorphism. How do you find the generators of this? The generators of C18 are integers prime to 18. What are those numbers? And they are definitely 1, 2 cannot be there, 3 cannot be there, 5, 6, no, 7, yes, 7, 8, no, 9, no, 10, 11, no, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6. So the number of 18th primitive roots of unity in GF19 is 6. Now let us take two polynomials in Z2 of x. Let two polynomials P1 of x equal to x cube plus x square plus 1 belongs to Z2 of x, and P2 of x equal to x cube plus x plus 1, that also belongs to Z2 of x. Then P1 of x and P2 of x are irreducible. Why? Because if you substitute the values of zeros and 1, the value of P1 of x cannot be 0. So there are two extensions here. There are two extensions of Z2x. One contains the 0 of P1 of x, the other contains the 0 of P2 of x. So let alpha and beta be the zeros of P1 of x and P2 of x respectively. Alpha and beta sits outside Z2 of x, C2. This is C2, 0, 1, alpha and beta somewhere here. It is not inside because these two polynomials are irreducible. So we have a simple extension here. One is, there are two simple extensions. So one is Z2 of alpha and another one is Z2 of beta. Both are extensions of Z2. And Z2 of alpha contains how many elements? 2 cube elements. Why? Z2 has 2 elements and this is the irreducible polynomial of degree 3. So it has got 3 elements, that is 8 elements. Here, same thing, Z2 of alpha contains, Z2 of beta contains 2 cube elements and that is 8 elements. Even though the polynomials are different, they are of the same degree. And that is the reason why you have 2 to the power of 3 elements. So that means Z2 of alpha and Z2 of beta have same number of elements. So what does that mean? Z2 of alpha is isomorphic to Z2 of beta. Actually, Z2 of alpha is equal to Z2 of beta that contains alpha such that alpha is a 0 of x to the power of 2 to the power of q minus x. And that is actually x to the power of 8 minus x.